Well, thank you for that wonderful introduction. I'm expecting somebody else a lot more important and august to stand up now and give the talk. I'd like to thank the KITP and Lars and Eckert for inviting me here. I'm having a wonderful time. It's fantastic for my research, and it's obviously a lovely place to be. So I'm going to give you a bit of an introduction to why we study avalanches, what are the sorts of avalanches, the damage and the destruction they can cause, what the point of the research is, and what's the underlying physics. And of course, these are natural phenomena that occur, very hard to get at places, they're unreliable, and if you're lucky enough to have something on the avalanche track, probably an avalanche won't happen. That's normally the best defense, is to put some science in the way. But if they do happen, then they might destroy your instruments. So with all these geophysical phenomena, it's very hard to get good data. So there's always a big push to try to get lab experiments that can scale and explain things. And these days, as well as lab experiments, we can do a lot of detailed work with simulations, which you can think of as a sort of idealized experiment. And I'm going to tell you a bit later about what these pictures here are at the side. They're not a natural avalanche. But as you heard, I first got interested in avalanches in 1993 when we were trying to climb this mountain. And what we were trying to do is climb up the northwest face. So I guess it's about 20,000 feet, and we were trying to go up this. And that's about 1,200 meters from top to bottom, and then go along the ridge. And we were supposed to be there post-monsoon, so it's up in the northwest of India, but the monsoon didn't realize the dates, and it kept on snowing and raining, and we were there for 2 months. And we keep going partly up and get hit by a snowstorm and go back. And then eventually we decided, we're just going to push on. We've got to get to the top. It'll be too embarrassing to go back and not having climbed anything. So we're climbing up here. We can't see anything. And then the ground starts kind of shaking a little bit. There's a bit of a roar. There's not much visibility. And I'm just caught by the edge of the avalanche. There's 4 of us on the rope. I was at the front, and I was swept many hundreds of meters down inside of this. Unfortunately, stopped just with my head sticking out, and the other people were just outside. And they dug me out, and then we were trapped in our tents for a few days before the weather cleared and we could get back to our base camp. So at that point, I thought, and especially after what happened later in the trip where we had another close escape, I should try to find out a bit more about this. Now, this is a photo of one of the biggest avalanches. This is off the side of K2. This went down by about 3 kilometers. So that's massive. It's probably several million tons of snow. This photo was taken by Pierre Béjean, who was a French scientist, also a very keen climber. He put up a lot of new routes in the Himalayas, and he sadly died later in an accident. Let's go back a bit. Now, what's nice about these as a geophysical flow to study is that we can actually trigger them. And what you see here is a little explosion. It's quite a long way off. It's a few kilometers off, so the sound is later. And we've thrown a stick of dynamite out of a helicopter. And they won't let me do that, unfortunately. And it's triggered a brittle propagation under this slab of snow. So all the grains start moving, and they're in solid contact. So at this point, it's flowing much like sand. But as it goes faster, there's a big speed difference between the sand and the air. So if you have the wind blowing along the beach, it can pick the sand up. And here we have a very excited French-speaking Swiss guy. Down here, this is the measurement mast we have at the moment, which is 15 meters high. And there used to be a 20-meter high mast here that got destroyed in 1999 by a big avalanche. Now, the Swiss are extremely good at engineers, and they know how to build things, and they over-specified this, and it still got destroyed. And that's because we didn't understand what was really going on in these avalanches. And now, this is going at over 100 miles an hour. For scale, this is 15 meters high, so you'll see how big it is. And now it's a very dilute mixture of the snow and air. But the snow, it's 1,000 times denser than the air. So even if it's a few percent by volume, this is still about 10 times denser than the air. So it's being accelerated, and it feels very little drag. So what we'd like to know is how fast this thing's going to go. And what damage is it going to do?
Did it take 2 shots to get that going? It looked like there were 2 puffs at the top.
Yeah, often they chuck out several. It depends. So, and then there's several different places they can release. So you'll go back and if you've blasted all of them and then you think it's safe, then we can go out and take observations afterwards. So that picture I showed you from K2, the height of that cloud was probably about 300 meters. And this avalanche we saw there, that probably got to about 50 meters. But would anyone hazard a guess about how high this one might be? So I mean, it looks pretty much the same. So the question is, can you guess how? Do you have an idea of what sort of height it might be?
100 meters.
Okay, well, it's good that you've got up and guessed, but this is only a few meters high. So basically, these things, they can look roughly the same over a wide range of scales, and that gives you some hope that, there might be some simple physics that can describe them. So we want to understand the scaling, and then if we can understand the small ones, which happen much more often, if we know the scaling, we can say what the big ones are also going to do. Now, those big powder avalanches are not the most dangerous ones. They happen in storms when people don't go out. But here we have some skiers, and they think they're on some nice powder snow.
Whoa.
And then they trigger this slab with them in the middle of it. And these kill around about 150 people a year in the Alps.
Did they live?
They were all fine.
Wow.
Well, they lived. I think they had some injuries, but they lived. There were people there, but they were extremely lucky. And it's very foolish to ski altogether on a slope like that. The correct thing is probably not to ski it if it's that unstable, but at least to go one at a time. So what's happened here is the wind has picked up the snow. So there's been very bad weather. It's like a snowstorm, and then it packs it in onto slopes of a certain aspect, generally away from the wind, the leeward slopes. And this is about 1 meter high, but these things can be many meters thick. And it's like a sheet of glass over sand. If you tiptoe out into the middle of it, maybe it won't break, but if you jump around a bit, the glass will shatter on the sand, and then it will start moving down the slope, and then it can form a powder cloud or whatever. But it's triggered by you being right in the middle of it. So that's why even if they're small, they're the most dangerous, or the ones that kill the most people. Now the distance, you can see this little skier here, the distance between safe, where everyone else has skied, and dangerous is very narrowly defined. So to understand why these slabs form, we need to have very accurate models of how the wind moves and separates and deposits the particles. And this is still not something that we can do with our current models. But this is a challenge that we're trying to work on to explain so we can get the best powder without other people. Now there's another type of avalanche that happens up in the high latitudes. It's in the winter in Norway and the Arctic. It's very dark, of course, or no sun at all. You build up all this snow, and then in the spring it starts warming up, the days get long, and the snow starts getting saturated with water. So it's sort of like a slush puppy type of a drink. And once the water gets to a certain threshold percentage with the snow, it suddenly loses its material. So there's sort of a state change between a solid with some water in and then a flow. And then it can go on very shallow slopes. So this at the bottom is probably only 5 or 6 degrees. You can see it started at a point, but it's entrained, it's dragged in all this other snow and water, gone through this building, and has killed 3 people. That's another type of one to try and model. Now this is what happens if the edge of your house gets hit by an avalanche. And the main research effort really goes into hazard zoning. So it's trying to decide on a map where is a red zone where no one's allowed to live and where you don't build any roads or any structures, and where are the areas where you can build houses, and so on. Now this is a dense avalanche that caused this particular damage. So here the snow's wet and heavy. It doesn't mix much with the air, and they can go quite slowly. But this is many meters of thick. The bulk density is about 600 kilos a cubic meter. Sorry, was it? So this will go straight through your car or your house. And that's what caused this. So we're trying to make these models, and they have to encompass this whole range of behavior, from slush flows to powder clouds to these dense blocks of snow moving down the mountainside. Now what we'd like to say is that the models we make and run on a computer, they're the best way of determining where it's safe to live. But the best way really is actually to look at the names on the map. And if there's a village called La Morte in the Alps, do not stay there on holiday. And if you look throughout the Alps, there are lots of villages with names like La Valanghe and all of these type of things, l'avalanche, which are mostly old words for avalanches, because over every few hundred years they all get hit by an avalanche. And the people knew that maybe they could have their cows there, but they shouldn't live. Now with holiday cottages, this one, the avalanche has taken out the ground floor and carried it along. So still the best way for hazard zoning is the historical record. But especially with climate change and climbing land use and in regions of the world that don't have the history, we really would like to have predictive models for where they're going to go. Now this is a fjord in Iceland. There's a big steep snow slope here, and this was a filling station for boats. So would anyone like to hazard a guess what's happened to this and why it's destroyed?
The tidal wave from an avalanche.
Exactly, yeah. So a tsunami came down this slope, triggered a wave that came across and destroyed this. And the largest avalanche-related disasters are of this form. There was one in South America where an avalanche went into a lake which had a dam at the end. It set up a travelling wave, a sesh that went back and forth. It eroded the dam, and then the whole thing failed. So you've got a big mix. You've got the snow, you've got all the water in the lake. It eroded all of the material in the valley, formed a debris flow, and it killed 20,000 people as it went down. So there's been several of these type of accidents. And there's a big effort now to use satellites for remote monitoring of unstable moraine lakes, especially in the Himalayas, where they're naturally dammed. But if they get too full, then they're very susceptible, and the trigger can be either an earthquake or a rock slide or an avalanche. Now, this is I think one of the most remarkable findings from planetary science over the last few years, where this is a photo of an avalanche on Mars. Now, if you were orbiting Earth taking pictures, you are very unlikely that you would ever see an avalanche. And this is taken by the HiRISE instrument on the Mars Reconnaissance Orbiter. And this is not normal water ice. There is a lot of water on Mars locked up as ice in the poles. But in the winter, it gets so cold, the atmosphere, which is carbon dioxide, freezes out. This is what we have here. We have about 1 meter of carbon dioxide frost/ice.
What is the scale of that image?
This is about 100 meters across. So this camera is amazing. It has about 50 centimeter resolution. And it's orbiting Mars. It has many spectral bands. It has a long line sensor, so a series of long line sensors, so it sweeps out these massive pictures. And now they've seen these things, they know where to look for them and what time of year. So they happen at spring, where the sun has got onto this face. I think this is the southeast face. So the carbon dioxide here has come off, and this avalanche has happened. And you can see actually that probably this other one happened first maybe, and then just over here, and then this one has been also similarly triggered. So this is carbon dioxide powder snow avalanche. We're not sure how fast these moved yet, but they could be moving much faster than ones on Earth. They could be hundreds of meters a second because the air density on Mars is so low. There's nothing much to retard them. So if we are to go to Mars, there's all sorts of hazards, including avalanches, whether there is skiing on carbon dioxide, ice and snow, or snowboarding, we don't yet know. So there's a big variety in avalanches. You can get very small ones, very large ones. The fastest measurements are about 250 kilometers an hour. Probably some of the ones in the Himalayas go faster. But there's all sorts of complexities that we're trying to understand. And as I said, the theories are not what we would like. I would not build my house based on one of my own predictions. But that is what we would like in the future. Now, can anyone here read Japanese?
Two.
Okay, right. Oh, this is one person and two people. So this character on the left, the top part of the character is rain, but the bit underneath turns it into snow, and then this character is collapse. So you put the two together, you get avalanche. And it's basically saying that several people were dug out alive, and one woman died later on the way to hospital. And this was a rescue and investigation that I was involved in, and what we wanted to know is, why did this avalanche happen, and can we predict them? So this is Japan. This is Hokkaido, the northern island. Sapporo, the main city where I used to work, is here, and then this ski resort is a couple of hours away. This is where the accident happened. This is called Haru no Taki, which means spring waterfall, and these are the waterfalls in the summer. Now, when you're out in the mountains, you can get a lot of information about where it's safe by looking at the vegetation. If there are very old trees, it's very likely that there are no avalanches there, or it's a very long return period. If there's areas where you have short, small, not so old trees, and other areas where there's nothing, there's probably a good reason why they're not growing on this flat land. So if you're out for lunch snowshoeing, choosing here to picnic would be a bad move. Now, one of the surprising things is this is almost completely flat, and this is still something that we struggle to get right with our models, is how the avalanches can maintain their speed here. And what these people did is they had their lunch, they saw the avalanche start, and this is the hole where one of them was dug out. They didn't have very far to go to get to safety, and one of them made it, but most of them, they left it too late to start moving, so they didn't think it would reach them, and 4 people were buried. They were all dug out alive from 3 meters down. The deposit was very deep, and one of them subsequently died. Now, because this was close to the university, we had a PhD student who worked here all winter, and his job was to take measurements and understand the snow. Now, you know, people say that the Eskimos have got 50 words for snow, but there's an international classification which has just been updated, which has more than 200 different types. So there's a lot of interesting thermodynamics there. And what we like to know is, you know, this is the prettiest snow and often how it falls, and it can change into these other forms depending on the ambient conditions. So over the winter it builds up on the ground, and if we take measurements of the weather, we can hope to try to say what it's going to do and if it's likely to be dangerous. So this is when the avalanche happened on the 27th of January, and in the week before it went from very cold to very hot, and then it dropped down to minus 15. This is very hot for Hokkaido in the winter, not for Santa Barbara. Got to freezing. Then it dropped 15 degrees and it stayed cold. And here we can see, you know, there was no snow, and then when it got cold, it went from 1.5 meters to nearly 2.5 meters. So the snow got warmed up, then it got very cold, and with 1.5 meters of snow. So there was cold snow on top of hot snow, and this drives the evolution of the snow crystals in a particular way. So this is how snow forms in this shape, and this is a snow pit. So if you dig through the snow, you can see what the crystals are at the top. So these pluses mean it's this pretty dendrites. Over time, these diffuse away, and it goes more like round balls, which is what these mean. You can also get these faceted crystals like this that are flat, and that's what these type of things mean. And we had snow pits at different times, and it was this formation of the faceted crystals, because of this temperature gradient, this is what failed and caused the avalanche to happen.
Excuse me, what exactly is a snow pit? Is it just a...
You dig a hole down, and then you look at all of the layers and take measurements of density, temperature, crystal type. Yeah.
So you can do it anywhere. It's not a...
No, you do it anyway. You go along and do it. And, you know, the PhD students in Japan are very obedient, so they will go and do what they're told, however horrible it is.
But it's not like a core sample.
No, you can take core samples, but they're not as good. You know, it's much better. If you really want to figure out what's going on, you've got to dig the pit, and it'll take you a couple of hours to do properly. If you want to do something rough and ready, you can do a core sample, but they're not so effective.
So having cold over warm snow as opposed to warm over cold snow?
That would be the same. It's the temperature.
The same metamorph.
Yeah, as long as you get a strong temperature gradient, they metamorphose towards these sheets, away from round grains. So the direction of gravity is not important locally for the change. So these are the results of a computer model that I helped develop. So here we've got the height and the colours of the different types of snow. So this blue and purple, this is the fresh snow falling. This is all old snow, which is stable. It's all round grains. And then because of the temperature gradient, it starts off as fresh snow, but it's trapped, and it forms this faceted layer. And this is where the avalanche happened, as soon as this new snow load was on top of this weak layer. So these type of models can tell you about the existence of these weak layers in the snowpack. Then if you know have some ideas of what forces it takes for them to fail, then when you get this extra loading, you can say that it's particularly dangerous.
So it's essentially the adherence between the layers. It's like a layer of ice with new snow on top of it?
It's not, no. So in this case, you can get weak layers like this. This is fairly stable old snowpack, and then if you have these grains, they're like sheets of paper. So you have a layer of about 1 centimeter here of all these flat grains like this, and these can slide. So they can be well bonded to the snow above and below, but then they slide within themselves. And it's partly because they stack up, so they have a little bit of volume, and then when they compress, then they just fail. So a little bit of loading, and then it will make a very slippy failure.
Is the thickness of the layer dependent on the amount of overburden, so it changes the thermal gradient across there as you?
Well, you can see by this downward curve, there's a little bit of compression, but that's not a main effect. It's basically that there is 15-degree temperature change over initially a few millimeters of snow. So we've got temperature gradient. You need temperature gradients of more than 50 degrees a meter or something, and the higher they are, the faster you get this crystal formation.
Why does it get thicker faster towards the right, where you have a bigger depth? You go from a half meter to a meter over.
Well, there's still this gradient, so the layer's growing. There's more and more of these faceted crystals forming. Okay, so this is another question for you, and there's a clue here in the scale. Who could tell me? And this is not a psychiatric evaluation. I don't want to hear anything too odd.
Avalanches in Switzerland.
Okay, that's a good guess, but it's not. Most of the north of Switzerland is fairly flat. It's not Switzerland. Okay, so this is
Northern Italy.
Also not a bad idea. This is in fact Iceland. And what Iceland is, it's this big dissected. So these are all avalanche incidents. They have an amazing historical record there. They're very good at keeping data. And this is what Iceland looks like over most of the coast. There's a very, very flat, narrow coastal strip. It's 800 meters up, and then there's this flat dissected plateau. And then if you get a lot of snow like they did in '99, you've obviously got to be pretty nervous about living down here. In '99, they had a whole series of accidents all around Iceland, and a lot of people were killed. This is what this place, Flattery, looked like. You can see the people, they've tried to move away from the steep slope as far as they could with their houses. These mounds here were designed to slow avalanches down, and this is a deflecting dam to try to keep it out of the way. Now, I don't know if any of you are engineers, but if someone says, build me some defences by my village, what are you going to do? So, this is what they did, but what's the best shape to build them? How big should they be? Is it just too expensive to make it safe, and should we abandon the place? I mean, the problem with a lot of the Icelandic coast is there's nowhere else to go. If you're going to move, you've got to go hundreds of miles away. So after these accidents, there was a big kind of concerted effort to try to improve, and this is what the centre of Flattery looked like after the avalanche hit. There's total destruction. Missed one of the slides. Sorry about that. So anyway, what happened? What the plan was then is to design a deflecting dam, but for that we need a proper numerical model. So you try to come up with the right equations, understand the rheology, and this will predict where the avalanche will go. And at this point, it was basically parameter fitting. It had some parameters, matched them up to match the debris, and then try different sized dams and rerun the model, see where it's going to go. And that's how they designed this new dam. It cost about $10 million or something. So it's probably a pretty good way of doing it. But the previous work, it was just sort of back of an envelope. No one knew how to do it. But we haven't had any avalanches as big as '99 yet. So that will be the true test.
Do the controlled avalanches have any success in releasing some of the snow?
They do, but it's very difficult to do controlled avalanche. So that's a great idea in a ski area where you can clear people away. But doing avalanche release above people's homes is very controversial. So,
only to the people in the houses.
Yeah, exactly. So, it's going to be better for them if you did it regularly. So in '99, there was this massive build-up. A lot of villages in the Alps were shut off. They closed down roads. And in Chamonix, which has the largest avalanche track in Europe, there's one that comes all the way down from Mont Blanc. It's like 3.5 vertical kilometers, 1 million tons. And the bottom of Chamonix, they have all these defences, but it's a historical record of the avalanche coming along the bottom and up the other side. Now there's thousands of houses. And when the avalanche did come down, some of them they'd evacuated, but they certainly weren't going to blast it. Because of the deflecting dam, some of the avalanche came off to the side and destroyed a load of buildings. Now, probably thousands of homes would have been destroyed without the defences, but the people whose houses were destroyed still still sued them. So they basically never blast with property there, that they do order evacuations sometimes. Now, one of the other things you might try and do is stop the avalanche starting in the first place. So these are a load of snow fences in Switzerland. So if we look at these close up, these are massive steel structures. It's about 3 meters high. You know, this is very expensive, very ugly, costs a lot of money, but is effective. Now, you can try to stop the things happening. This is a church in Davos at Frauenkirch. It's very famous. So there's not much. These other buildings are a fair bit lower, but as you can see, there's no windows, no doors. This is very thick, and it's built like a ship. So little avalanches will come down here, and they will flow past this building. So this is a simple but effective thing. You can harden your structures. I think it's the 17th century.
Wow.
Yeah, it's been there a long time. And further away, there's a lot of buildings, but this is the only one for a few hundred meters. And it's built. They were obviously very God-fearing because it's built right at the bottom, looking up at this avalanche track. They trusted in their architect as well, I guess. Or maybe there were a lot of other churches first that got destroyed, and they kept on making them bigger. Oh, so this is the dam that they built to defect at Flattery. So, and they were the simulation result. So here was the simulation, but without the dam, and here is the simulation with the dam. And when we get an avalanche of that size again, we'll be able to see how accurate these things are. Now, if we want to make these models, we have to try to figure out exactly how does snow flow. So one way of doing it is to get a chute and put the snow in. So this is a 25-meter chute in Switzerland in Davos, and we can change the angle. And we can, first we shovel the snow out, then we shovel the snow in. That beep is when the experiment should start. Then we send up the Swiss PhD student, Felix, who has now switched research topics into quantum optics. You send him up to try and get the snow to release. So we can learn a lot from that. So, you know, water, we know it flows as a Newtonian fluid, and we have very good equations. And for snow, by taking these measurements of forces and velocities, we can try to make a model which will describe that. And we did a lot of work on this shoot for those aims. But as you can see, that's a difficult experiment to do. It's not very well controlled. So we could also try something on a much smaller scale. So this is a schematic of an experiment I did, and we could either drop snow down the top. This is 2 meters by 1 meter. We would video it. We'd take other measurements. This shows you at the side. So we could drop the snow down here, or we could use polystyrene beads. And we want to see, like you saw in the avalanche in the video, the stuff moves down the slope as a dense flow and then mixes with the air and becomes a powder cloud. And once it's a powder cloud, it can move much faster. So we wanted to try and get that in a laboratory setting. So this shows you a large amount of these grains. In each clip it's the same, but as the angle increases, you'll see that they get higher and higher, and that's because they're mixing with the air and becoming suspended. So this reproduces the basic physics in a very simple and controlled setting. And that's past 90 degrees. It's past vertical, but it still looks basically the same. So when I asked you before, can you tell the size of these things from the photo, the answer is no. And you can't really tell the angle of the slope either. If you look very carefully, you'll see that the nose of it varies with the angle. But that's about it. The rest of it is pretty much the same. So we can get those nice type of things. And here we can control exactly the number of particles and the slope. And we can try to say, how does the speed depend on the amount of material there? Because that's what we'd like to know from an avalanche. If there's twice as much snow, will it go twice as fast? If it's twice as steep, will it go faster or will it go slower? So here we have the speed that we measured, and if we divide it by the 6th power of the volume and square root of g, we get what I call a non-dimensional velocity. And these are many different orders. This is a couple of orders of magnitude, and they all end up with the same thing. So what this is telling you that the speed of the avalanche goes as the 6th power of the amount of material in it. And remarkably, this is the slope angle varying It doesn't really change with the slope angle. Now, if you're skiing and you ski on a 30-degree slope, you go at a very different speed to a 50-degree slope. So why is this not altering? And what happens is, if it's a shallow slope, it doesn't mix much with the air, so it's very dense and it keeps one speed. If the slope is steeper, it mixes with more air, so it's more dilute, so it experiences more drag. The net effect is they go almost the same speed. So with this simple experiment, we have a prediction. We understand the scaling, we understand the dependence on the slope angle, so we have a prediction for whatever size of avalanche and slope, how fast it should go. And in general, we can make this more complicated and look at how it should vary as it goes down the slope and so on. Something else we can do, also direct simulations. So we can imagine this is a mixture of snow and air that's moving down the slope under gravity. And now you can do these simulations where you're directly solving the equations, you're trying to include all of the known physics and see what happens. Then you could even, some of the work Eckert's been doing, you can even put obstacles in the way and then actually directly calculate what the forces are. So these sort of direct simulations are tremendously useful. Give us a way of doing idealized experiments which are hard to do or make it difficult to actually take the observations.
So, excuse me, but on that picture, why does it churn versus run linear, given what you talked about for the flat grains? You know, you said when the flat grains get to be a certain distance, that's what then causes the shearing. But when you look at that, it almost looks like they're creating wave patterns versus.
Well, this is at a later stage where the thing's got faster and it's already mixed. So here, the grains are at a low density. They're mixed up with the air and just going along. And all this other physics would be in the bottom and wasn't included in that model. So that's a slightly different case. Now, what you start seeing, though, in these simulations is that when you go to a 60-degree slope or something, let me show you that again. That happened very quickly. Something completely different happens. It goes along a bit and then it just disappears. And this is not what happens in the experiments or in real life, and it's still something we're working on as to what's different about these things. And there's a variety of causes. So they're great in a lot of ways, simulations, but we still don't know the best way to apply them in all situations. Let's just go over those. But they do at least give us this basic picture. I said from the experiments that the speed, so here we have the front speed non-dimensionalized in some way as a function of the slope angle. So we can vary these parameters. These are in some ways related to the size. And again, we get that the speed is roughly constant. So this is true for these small 1 or 2 meter long experiments and these simulations. And we can think of these experiments being as any size we like, just depending on the amount of material or the gravity. Now this is back to our test site in Valladolid. This is what one of those sticks of dynamite looks like when you chuck it out. Here we've got a side view and we see this slab motion again coming down. This is filmed from the helicopter, so you get a really good view of the tail of it here as well. Now, one of the nice things, we have all sorts of instruments now, and there's been a big sort of breakthrough in the last few years. There's a lot radar systems, for example, that used to only be in the realm of the military that would cost millions of dollars. You can now get for 100,000 or whatever and give you tremendous data. And there are also these really nice thermal cameras. So these often look like sort of horror movies with someone stalking somebody else. But this is an avalanche with a thermal camera. So the color here is the temperature of what you're seeing. So this region is all cold, and because the snow gets warmer as you go down, where the avalanche is, it's pulling up the snow from lower down in the snowpack, so that's showing up as these red traces. So these are the deposition from the dense part, and then you saw this powder cloud blowing away.
What's the difference between the warm and the cold there?
The warmest temperatures here are -9, and the coldest -23.
So what, that contrast that you're seeing right there in the middle of the image is about, what would you say, about 5 degrees?
Yes. So I mean, this is the first frame of that, so you can see that Most of the temperature variation here is just due to the aspect ratio. Then as you went down through the snowpack, and after these experiments, we went out and we dug snow pits to look at the temperature of the snow, see how it varied. And then when we see this stuff appearing on the surface, we know how far down it was brought up from. Now, of course, there's also energy dissipation in the flow. Let me show you this other one as well. Here the avalanche happens over there. I just show out very clearly. There's also energy dissipation going on, which will also raise the temperature by a couple of degrees. So there's a cloud, and then there's this denser layer underneath. And here you can see it pulling up snow from further down, which is very cold, showing all this blue stuff.
Have you evaluated the effect of solar loading on avalanches?
Well, it changes the evolution of the snow grains, so whether they're going to start or not. So that's one of the things that goes into these snowpack models to assess the stability.
So, I mean, the side that faces away from the sun is less or more vulnerable to avalanche?
That would depend. So in the spring, when you get a lot of radiation coming in, you start getting these wet snow slides, so the south-facing slopes will avalanche. But generally, the warmer the snow is, the more quickly it can metamorphose, and it tends to metamorphose and form bonds to a stable way. So mostly south slopes will stabilize very quickly in a few days, where the north slopes can stay dangerous all winter. So there's complexity there, but it's understandable. Now this is one of the pictures from the beginning. This was a Japanese PhD student, and this was a foolish English postdoc, first out in Japan, who was told that this was a good thing to do. So the Japanese, they wanted to test out the instruments that they use in the mountains on a full-size scale, and again look at this transition from a dense flow to a suspension current. So here you're about to see 650,000 ping-pong balls, which is probably the most that's ever been in one place outside of a factory. These orange ones are practice balls. They're about 20% bigger. So you can also look at segregation and other things with them. And we had a whole load of sensors mounted on the slope and a lot of video cameras. You see this characteristic head, which is the same as the natural ones in the lab experiments and the simulations, and then a thin tail. The fastest balls were 20 meters a second and left bruises. So these are a lot of our instrumentation here.
Is that a ski slope?
It's a ski jump. It was used from the Sapelo Olympics. It's a normal hill.
Did they have any protection there?
No.
Just
We were tied on.
Just
It's quite steep. Well, this was me, in fact. So we were tied on here to stop ourselves slipping down with it.
Who did the cleanup?
Well, you'll see that we would get all the snow scientists in Japan would come, and we would enthusiastically advertise it to local schools and get as many people along who wanted to come as possible, and collect them all up and put them in bags and take them up to the top again. And a big thing here was to look at this scaling analysis. You know, if you've got 2 balls or you've got 200,000, how does the speed scale? And what I showed was this lab experiment that basically goes with the 6th power of the volume, or the 6th power of the number of balls. So here we have the speed of these ping-pong ball avalanches, showing you that again it gets this 6th power scaling. So we can reproduce it basically with simulations and with small lab experiments and with these big ping-pong ball experiments as well. And if you want to go further and look at the evolution along the slope, put a little bit of maths in. We've got the acceleration of the avalanche, the acceleration down the slope. We have some friction with the ground. We have some air drag, and we have some centrifugal effects and some air drag. We have a very simple ODE. This looks like a horrifically complicated system as it is, but as I've shown, the scaling gives you a rough idea of what's going on. You can actually get a very good fit. So these are curves. These show you the velocity of these avalanches down the slope and comparison with this simple model. So if we wanted to describe all the features, we'd have to do something much more tricky. But because we basically conserve mass and momentum, we put a little bit of empirical knowledge in, we can get a pretty good match.
Does that equation give you the to the sixth power?
Mm-hmm.
I think it does. Well, that's pretty classical. I mean, you could do that in a...
Yeah, no, I mean, it's not rocket science.
Yeah.
But yeah, it's ping pong ball science. Even rocket science isn't rocket science anymore. Now they teach this to undergraduates. So.
Did you find a difference between the slightly bigger diameter?
Not in that experiments, but if you do other experiments, you tend to find them on the top of the deposit. It's sort of the Brazil nut effect. They segregate up to the top. So we could apply the same model. These dots here are data points from validation, so the real avalanche. There's a few more ingredients in the model because you have to take into account entrainment and deposition of snow, both at the bottom and air entrainment. So these are the fits. And, the data is hard to get. There's a lot of scatter. But the basic model predictions for these three avalanches are okay. So here, there's clearly a bit of trouble with the data, but it's extremely difficult to get. But now we have a very new radar, which will give us much better data in the future. So this is the same model, and it works for the avalanches and for the simulations and for the lab experiments, and is never before repeated. So the last little bit is, most of the time you can't get to see an avalanche taking place. And when you're looking at other geophysical flows like rock slides, pyroclastic flows, and all these photos from things on Mars, sometimes you see them happening. Mostly all you see is the deposit. So what can we learn about the deposit, about the flowing properties? So this here, you see there's a lot of large blocks. This is me walking up here afterwards. You see a lot of large blocks on the surface. So this is the segregation effect again. And this turns out to be quite important for increasing mobility of these flows. And what we did here is we had this laser scanner. This is a fancy piece of kit we put up in a helicopter, which has a very accurate GPS system. So we would fly over the whole track, take very accurate measurements of the height, blast the avalanche, and then measure the surface height again afterwards. So there we can see the change in the height, and that tells us the net difference between the erosion and the deposition of the snow. And we know far down the slope it's all going to be deposition, and far up the top it's erosion. So then you get a sort of a map like this. And blue, some of these places here, there was 7 meters of snow had deposited, and it's all been eroded. So this region is all erosion, the blue region, and down the bottom it's all the deposition. Also down the bottom we have a bunker with a lot of instruments in, and we have some people there who operate them. As you can see here, there's 10 to 15 meters of snow in this case, and sometimes it can be more. And sometimes you have to go back to the bunker afterwards and dig out your colleagues who've been there. In 1999 there were 7 meters of snow on top of here, and the snow had packed in so hard they couldn't dig them out. They had to go off and get chainsaws. Dieter Isler, who's one of the participants here, he was in the bunker, and he said they had pains in their ears and they were kind of nervous because it took so long for people to get them out. The bunker is well built, but this is Martin Kern and us getting him out afterwards.
Because it'll refreeze into ice.
Yeah, that's it. It melts a little bit and then it freezes solid, and you can't dig through it. So I mean, you'll never get yourself out of an avalanche. You need your colleagues or friends to dig you out. So these show you the sort of average snow depth variation for a couple of avalanches as a function of the slope angle. And what you see is there's this division between slope angles where it erodes and slope angles where it deposits. And where it's steep, of course, the snow doesn't deposit, it will also move. And then there's this range of angles where it will build up. And here we just have this net deposit depth for these avalanches again, with curves from a very simple model. And in this model, all we have the component of gravity times the depth of the snow down the slope. And it's balanced by a cohesive force in the snow. The snow grains can stick together. And then a frictional component, which is just friction times the normal force. And they give you these curves which agree with the depth very well. So that means if we go out and we see the deposit and we measure it, we can deduce properties about the flowing snow. And when we do this, we can compare them with our chute measurements and everything, so we can get some idea of what are the real dependencies of C and mu, and therefore use them for our actual models. So this is sort of an inverse problem. And of course, we'd like to do the same thing with all the deposits we see on Mars and pyroclastic flows and so on.
Does it imply that if you climb on 30-degree slopes, you'll never get buried deeper than a half meter?
Well, you won't get buried there, but you'll get carried down to the bottom, and then you can be buried very deep. It depends on the snow. These things depend on the temperature quite a lot and the water content. But yeah, for this dry snow, then yes, you won't be buried there. But that won't give you much satisfaction, though. Okay, so this work is done with a huge number of other people over many years, including Eckert, who's in the room. So I'd like to thank all of them, and I'd like to thank you for being a great audience and for your questions.
We asked a lot of questions, but let's take a few more.
Hi, are you familiar with the term avalanche in the electronics world?
Avalanche diodes and
yeah, I mean, even before there was avalanche diodes, there's things like lightning and gas discharge tubes and so on. Is there any relationship with what you're looking at?
Maybe in the initial failure. So you can imagine, you've got a distribution of strength in the snow layer. And if you put some forcing, when is the thing going to fail? So it's a sort of a percolation problem. And I think these things are similar. As soon as one part of it fails, there's more stress on the rest of it, and then it can spread out. So in this brittle failure, yes.
I was just wondering whether you might even be able to use that as a simulation, but maybe it's a totally different...
Well, the initiation, I think probably the same underlying maths, if you've got a random distribution of something, when will it fail, at what load point, and what are the statistics of that? So that would underlie it as well.
Backpacking in the high Sierras, there's a trail down near a chute, and there are redwoods in the chute, and they're broken off like matchsticks.
Yeah.
So it's an avalanche chute. And in the direction, in the vector at which the avalanche goes down, have you done measurements of pressure per square inch, dependent on the density of the snow at per one point that it's going past?
Yeah.
To show what kind of force it takes to knock over those large redwoods?
People look at trees a lot because then you can use them for back calculations. Where's the slide I want? Here. So this is our measurement mast in Valladolid. So we have a whole lot of sensors. These discs, these measure the impact load. So they measure the force of the snow flowing around it. And we also have probes, capacitance probes, which measure the density of the snow, and also things for velocity. So we can measure all the forces. This here has larger force plates, so a lot of the measurements focus on exactly this problem.
What's a typical value?
Oh, what's a typical value? Oh, crikey, let me think a second. Hundreds of kilopascals. Yeah.
How tall is that tall one?
This is 15 meters.
And that will survive the avalanche?
It has so far. But there haven't been any as big as 99. But the one in there before was 20, and it was really overspecified for the largest forces. And this one has been, possibly it was a resonance effect that actually caused it to fail.
Is that freestanding or guide?
Oh, there's a big concrete. There's no guides.
No guides.
There's no guides. So,
when I was a kid, used to go skiing in the late 40s and early 50s at a place called Badger Pass, which is on the north side of Yosemite Valley. And they had a World War II 105 howitzer that they would shoot off before anybody went up on the slope.
Yeah.
And it worked.
Yeah.
You could see these avalanches starting. And they usually do it, you wouldn't get on the slopes until after 10. So there was something to do with the heating too, I guess.
Yeah.
But is sonics used to initiate avalanches on purpose?
Yeah, well, these old military artillery pieces are used a lot in the States, but I believe that they've got the problem now that the ammunition is all obsolete and there's no longer any of it left.
Whoa.
And modern ammunition, is much more expensive. So I think I'm no longer sure if they can do that. But that's what Rogers passes all of these places. To build defensive structures is very expensive, and you have to maintain them. And this sort of depends on your budgeting procedures, whether you think it's better to go along and blast every few weeks or to build something. But they would basically
hand charges.
you can use hand charges or artillery, and people use compressed air things and gas as well.
Yes.
Can you use ground penetrating radar to do larger area mapping, or is the critical layer too thin?
So in these experiments here, afterwards we dragged GPR across here. It's a ground penetrating radar. And in validation we have sort of the opposite. We have some radar built into the slope, so they bounce off the layers of snow as they flow over.
But does it have enough resolution? Because it sounded like that critical layer was very, very...
Well, we get resolution of about 1 centimeter.
That's pretty good.
So, and with the older system there, I guess you could get better resolution these days, but not by much.
Can you contrast pyroclastic flows to avalanches? I think the density of lava is a lot higher. So
there's a couple of things with the pyroclastic flows that are different. So you've got two sources of things changing the density. You've got the temperature of the hot air and the rock. So when the thing comes out, you've got a mixture of hot air and rocks, and they tend to rise up. And then as the rocks, and then possibly hug the ground, overall normally the density will be larger. So it will move down very much like a powder snow avalanche. But because there's all these large rocks into it, over time they drop out and they form a dense rock slide along the bottom. And then the mean density of the material that's left is mostly air and it's hot, so then it rises up. So you'll get the thing coming down and it will look like a powder snow avalanche, and then it will take off and you'll get a rock slide afterwards.
And they move quite fast as well.
Yeah. They're really hard. The reason these are better to study is they're much less destructive.
They get grad students.
Yeah, they're more... And they're more repeatable because they don't change the ground much. You know, each volcanic eruption will be completely different, and they can deposit tens of meters of material, and you can't really put instruments in their path that will survive. Or if they do, they're buried under all this stuff and you won't get them out.
How many times a year do you get enough snow to have an avalanche?
We get about 25 avalanches a year, different sizes. And a lot of that is only this winter that we've discovered there were so many, because a lot of them happen repeatedly in the storms. And at the bottom now we have a phase array Doppler radar pointing up, and it's 5 centimeter wavelength, so it goes through the powder clouds, through all the weather, and it looks at the dense snow. So we can see these small avalanches happening in the storm and track them the whole winter.
What about the physics of the initiation of the avalanche? Has that really been studied?
It's been studied. It's not something I know so much about. It's been studied, but it's not really understood or that well modeled, I would say. But I think there'd be a lot of interesting work that could be done there. The problem is that...
So is it believed to be shock wave or a net pressure that's just pushing on something that has a low friction?
Well, it depends on the case. So the slab avalanche, it's some sort of, you've got this brittle elastic material, and then it's how does the fracture propagate and then break up. For the loose snow, it's a little bit less clear how they fail. Even with dry granular material, it's not that clear whether they're failing at a point and it's spreading out, or whether there's some larger region failing. And that there aren't... The tricky thing here is to have a rheological model that can have the solid state and the liquid state and a yield criteria before that. And there aren't really... People still argue about yield criteria for the most well-known material. And that's the problem.
Last one. What about the contribution of the material that it's carrying down with it, trees as well as dirt that it picks up? I mean, that obviously makes it more destructive.
Yeah, that's very bad news.
It's pretty variable.
Yeah, that's very bad news if you're in it. I mean, a lot of the people in avalanches are killed by the trauma. And that's partly the snow, but a lot of it's to do with trees and rocks. And they will pick up all of this stuff
like
as
mud
well.
flows, floods, even tornadoes.
Yeah. They will pick up and transport things.
Thank you.
When you were in Avalanche, did you notice the temperature change?
Thinking of other things.
What's an average value?
I noticed a large increase in my heart rate.
Okay, well with that, let's thank